Physical Applications Part 1. Work can be described as the change in energy when a force causes a displacement of an object. When you lift a weight above your head, carry a refrigerator up a flight of stairs, or push a stalled car, you apply a force that results in the displacement of an object and work is done. If a constant force F displaces an object a distance d in the direction of the force, the work done is the force multiplied by the distance. Work equals force times displacement. Let's talk about units. A Newton is the force required to give a 1 kilogram mass an acceleration of 1 meter per second per second. A joule is a 1 Newton meter, the work done by a 1 Newton force over a distance of 1 meter. Calculus is needed when the force varies. Suppose an object is moved along the x-axis by a variable force F that is directed along the x-axis. How much work is done in moving the object between A and B? Looking at the graph, we can see that at each point x on the interval, the force has a different magnitude. As we have done before, we will look intuitively at how calculus is used to address the issue, and my explanation should not be taken as a proof. But here's the idea of what's going on. At each point x, the force F is applied to the object, resulting in the displacement of the object along the x-axis for an infinitesimally small distance of dx. So at the point x, there's a force F of x resulting in dx. So the work done for that one instant, for that one point x, the work done is the force at that point times the displacement. Adding up all the different pieces of work, if you will, adding up all the pieces for every point from A to B, we get that total work is the integral from A to B of the force times dx. Suppose an object is attached to a spring on a frictionless horizontal surface. Let x be the position of the object, where x equals 0 is the equilibrium position. To stretch the spring to a positive position, a positive force is required. To compress the spring to a negative position, a negative force is required. In other words, the force required to displace the spring is always in the direction of displacement. Hooke's law states that the force required is K times X, where K measures the stiffness of the spring. Suppose a force of 10 newtons is required to stretch a spring 1/10 of a meter from its equilibrium position and hold it in that position. What is K? Well, we're told that 10 newtons equals K times 1/10 of a meter. Solve for K, and we get that K is equal to 100. So f of x for this spring, f of x is equal to 100 times x. Okay, now working with the same spring, how much work is needed to compress this spring a half of a meter from its equilibrium position? So x is going from 0 to negative 0.5 because we're compressing. And so I set up my integral from 0 to negative 0.5. I integrate and evaluate. And that's going to be in joules. How much additional work is needed to stretch the spring 0.25 meters, so a quarter of a meter, after it has already been stretched a tenth of a meter from its equilibrium position? So it's already been stretched to 0.1. We stretch it another 0.25. So now the spring is going from 0.1 to 0.35. And then you integrate and evaluate, and again it's joules. Another common work problem arises when the motion is vertical and the force is the gravitational force. So force in that case will be mass times g. This type of problem becomes more interesting when the object being lifted is a body of water, a rope, or a chain, for example. Different parts of the object are lifted different distances. Suppose a fluid, such as water, is pumped out of a tank to a height of h, h being the distance above the bottom of the tank. How much work is required? We divide the tank of water into layers. At level y, the layer will travel a distance of h minus y. So it's going to go from y up to h. So the distance is h minus y. So work is force times displacement, and just replace the displacement with h minus y. Now, motion is vertical, and so instead of F, we're going to put in mg. All right, let's work on the mass. For a fluid, mass is volume times the density rho of the fluid. So volume is volume times, so mass is volume times density. So what's the volume of the layer at y? For a given value of y, the volume of the layer at y is going to be A of y times D of y, where A of y is the area of the face of the layer, the horizontal face. So you just take the layer and turn it towards you. And A of y is determined by the shape of the tank at the height y. So your area is going to change as y moves up and down the axes. And dy is the thickness of the layer. Putting all this together and adding up the work for each layer. So we've got our first layer. Just put AY dy in for volume. So that's just for one layer. Let's add up all the layers, and this is what we get. The work required to lift all the fluid to the outflow level is given by this integral, where B is the height of the fluid. So B is the height of the fluid. Rho is the density of the fluid. G is your acceleration due to gravity. And A of y is the area of the horizontal slice at y. And then, of course, don't forget H. H is your outflow level. In the next video, we're going to do an example using this formula. Take care and have a great day.